Hello everyone, my name is Nak Nguyen, and I'll be introducing our capstone presentation and integrative methodology to securing IoT health applications. The team members of this capstone project are Lawrence Chang, James Hutchins, Nak Nguyen, myself, and Emmanuel Bolresh. This is the agenda for our presentation. I'm going to go over briefly our motivation for our project, the objectives. I'm going to go over some introduction and backgrounds into IoT security, and then our methodology to our applications and our systems that we developed. Finally, some roles and deliverables, and then the project schedule across both semesters. And lastly, I'll introduce our references and then open up to questions. For our motivation, the quote has, "The IoT has more potential than any other previous competing paradigms to directly impact the safety of human lives for better and for worse." So in IoT security, this incoming new competing paradigm, there's a lot of security issues, some listed here, that in regards to IoT, it is available anywhere for consumers and hackers alike. A lot of the IoT security devices have default passwords hard-coded into their systems. Furthermore, sellers cannot afford security and consumers want to buy cheap devices. This leads to a lot of outdated and unpatched devices, which leads to and results to a lot of massive vulnerabilities. And so these are the main takeaways for our motivation. The current state of IoT security is not standardized. So we aim to introduce security in the consideration of the design, and we seek to provide the guidelines through demonstration of our IoT networking systems applications. This is our three main objectives that we aim to achieve in our project. We want to provide security for an IoT healthcare application through focusing on secure communications between nodes in the network. That means the communications between the smartphone, the smartwatch, and the hosted cloud services. Then we want to provide integrity for the data, whether it be at rest in the database or sitting at the end user's smartphones. Finally, we want to provide authentication for the users, and we're going to go over some of the protocols and methods we aim to do that. So here's a brief background into IoT. It's the internetworking of physical devices or things embedded with various technologies. As of 2016, there is this estimated 15 billion devices and projected to be 200 billion devices by 2020. There needs to be a focus on the integration of a lot of the security measures of users, because all IoT devices are connected to the internet. There's a lot of confidentiality and integrity issues. So in our devices, we aim to increase a focus on the application layer and its security. There's obviously some more motivations through the recent exploited IoT devices, such as the CCTV camera botnets. So here's the current state of IoT application layer briefly. There's no standard during the construction of IoT applications. There's an influx of data through many HTTP packets, and some of the data that's being transmitted across is sensitive. There's also a lack of data access permissions, which we also aim to ensure and provide. So our application will have many users, or is open to many users, and thus we need to ensure the authentication to legitimate users. And our application must also handle vast amounts of data being transmitted securely and both efficiently. So here's briefly a server-side design. We're going to be using a lot of Amazon Web Services. We're going to be using an Amazon engine to host our app, as well as to communicate with a database server using MariaDB, which we'll discuss later. And then these hosted web cloud services will be speaking to our endpoint clients, and each client will have both a smart phone application as well as a smartwatch, where it will be collecting data and transmitting it to our smartphone, which will then be communicating with our hosted applications on the cloud. So for the database server component of our IoT network, we decided on using MariaDB, which is the fork of just MySQL Server 5.7 with some minor optimizations. And then on the hosted on the cloud will be a database containing tables with entries for username, step count, and timestamps. Username will be obviously used for authentication later on to associate the following health and fitness data, step count, and timestamp. And for the phone application, which is our health and fitness tracker, we use this phone application to store data securely and then transmit this into our cloud. This serves as our environment for sending and receiving. The phone application, in order to achieve our authentication objectives, we aim to use a third-party login authentication using open authentication with Facebook. We also aim to use transport layer encryption and communicate only via HTTPS. Our phone shall also have features that monitor, collect, and display data from the smartwatch, such as heart rate, step count, and the distance traveled. And our smartwatch shall collect, transmit, and data to the smartphone. It will also be displayed in the smartphone application in real time. Okay, these are some of the device specifications that we use in our project. For the smartphone component, we decided on an LG Nexus 5 because it hosts a standardized Android operating system, and we want to make this as ubiquitous and encompassing the most users as possible. We picked the Moto 360 Sport because it has a compatible Google Fit API that we wanted to communicate with our Android device. And then on the server side, we use an Amazon Web Service Cloud Hosting NGINX web server and a MariaDB because once again we found it compatible with the technologies that we use, and it's running an optimized MySQL server, which we already had prior knowledge in using.
I'm Lawrence, and I'll be discussing the network model here. As you can see, the network model on a base consists of 3 nodes. We have our servers running hosted by Amazon, the AWS servers in the cloud, and then we have the user, which associates with the smartphone and the smartwatch. And how this generally will work is the smartwatch will be collecting some kind of health data, and the smartwatch itself will be correlating with the smartphone. And what will eventually happen is when the user decides to update his information or upload his health data to the cloud, we'll be using HTTPS, uploading to a database, posting to a database essentially, and storing it on the cloud for long-term analytics. So one of the first things we wanted to cover was how do we make sure that we maintain the integrity of the data, and this was answered in several instances. For example, data at rest would be encrypted by Amazon Web Services just by using their cloud services. So if in any case some other third-party user were to perhaps CD into our directory, our data would be encrypted. And then another feature we added to ensure integrity of some kind was access control lists, mainly for the database. So the way we implemented our database was in a way such that we made a user that did not have admin privileges and in fact only had write privileges. He could only post to the database. So no read privileges means that a potential attacker could not use our database user to read data that he was not supposed to. So the second part that we wanted to get into was how can we start this network itself, and we decided to use an Android application as a jumping off point as seen here. So the technologies we used to develop this application were of course Android, and we used Java written in Android Studio's IDE. We decided to choose this because it was open source, Google supported it. A lot of APIs were actually very compatible. For example, we were to read sensor data using Google Fit, which of course goes hand in hand with Android Studios. Another thing we wanted to mention was what kind of smartwatch were we going to use. So of course we picked the Moto 360 as explained before because the smartwatch operates on Android Studio, again adding another level of compatibility. This slide here goes into how we communicate between phone and watch. So we use Bluetooth, a low energy Bluetooth protocol. The phone and watch communication is assumed to be secured just through that protocol itself. We don't really touch that. We mainly focus on Wi-Fi and internet security. We utilize ad hoc APIs and secure protocols that, as mentioned, the Android Bluetooth API. And so now we go into how do we want the phone to communicate with the server. And over here, these were the two finalists, so to speak, of which protocols we wanted to use. And we took many things into consideration, such as power efficiency, security, the header size was a big one, and of course reliability. And this is a table of us comparing HTTPS with CoAP, which is an emerging Bluetooth protocol. And you can see that all in all, CoAP seemed to have an edge over HTTPS. Power efficiency, CoAP was designed to be low energy use, and the 33,000 compared to the 31,000 is a huge difference. The header size was also much smaller than HTTP, but in the end we decided to go with HTTPS. So HTTPS was primarily chosen because we wanted to focus on security capabilities and reliability. And you can see here, HTTPS is built in with TLS. It's built on top of that layer. It ensures that no outside party, no man in the middle, so to speak, can see the traffic going on in the network. We also chose it for reliability. TCP is known for error checking and packet recovery, ensuring that all our data is always either sent or we get an error if it was not sent. So to go a little more into the user authentication part, Facebook was chosen to accommodate a large user base, as said before, and it was available through Facebook Android SDK, which made implementation a lot easier. So the way that the authentication scheme works with Facebook login is there are 3 choices depending on prerequisites. So if the user has the Facebook app on his or her phone and she is logged into that application, in that case, Facebook will immediately log them in but ask the user for permission to use our app, and that's how the first scheme goes. Otherwise, if Facebook is installed but you're not logged in, our app will actually redirect you to Facebook's application where it will tell you to log in, and that's when OAuth, of course, comes in again, in which you give permission to Facebook to use our application. Finally, the last scheme is if the user does not have Facebook installed at all. In that case, it will open up a web browser-like interface where the actual website of Facebook.com is pulled up, and you as the user would have to log in and then, of course, give permission. And this was our authentication scheme. It was easy to use. It allowed users a more familiar face, and they were able to rely on Facebook maintaining their data, as we, the app developers, had no touch in their passwords and whatnot, sensitive information.
Hi, I'm James Hutchins, and I will be covering the remainder of the project. For the evaluations of the deliverables, the server specifically, we set up an SQL and database like we said we would, and it had most of the fields we had said. We had originally decided we were either going to do email or a unique identification number for the users, but then we found out we could receive the username from the Facebook application, and we decided that that should be unique, so we used that instead. We also stored the step count and the time that step count was sent up to make sure that the data seemed reasonable. We were also originally planning to store heart rate and calories burned, but didn't get around to it. On the phone side, we had the ad hoc Bluetooth connection. We had the open authentication third-party Facebook, which originally we were planning to make our own login, and then we determined that one would be more secure and more trusted by everyday users because we read that in an article. We used the HTTPS transport layer because we determined that the security that it provided over CoAP was more important, and we chose that. We have a email enrollment, but what it really is it's basically the username's fetched from Facebook and stored into there, so each person's still identified by a unique piece of information. And then we were planning to add some more security to the login with like a unique PIN that would be generated that they could enter, so 2-factor authentication, but we didn't have time to get around to it. Our app was also able to monitor and display data from the smartwatch and smartphone that included heart rate, step counts, and distance traveled. We were originally planning to also include calories burned, but didn't get around to it. So the results, we were able to complete most of the project objectives that were set out for us. We were able to secure the communication between the phone and the watch and the phone and the server. We were able to ensure that integrity of the data by putting the timestamps in to make sure that the data seemed reasonable. The steps should only go up because it was cumulative steps. It shouldn't be reset to 0 at any point. And we were able to, and TCP protocols also try and confirm integrity of the data by having their own hash that is checked and making sure that none of this information comes in out of order. And we were able to authenticate users using the Facebook login.
Hi, my name is Manuel, and I'm going to walk through the lessons that we learned during this project. So first of all, we were behind schedule at one point almost an entire month. The way we overcame that was a few of the things that were giving us complications, such as learning the completely new Google App Engine by switching over to Amazon Web Services, which several of our users were more familiar with. We were able to overcome some difficulties. Also, we rescoped a lot of our original intentions. We made a lot of consideration when creating our model for IoT. For example, doing the research for HTTPS as well as versus CoAP. And here is a list of our references. We looked through several research papers. And then, for example, here our research shows a lot of references from reputable sources such as Bruce Schneier about the issues that we face today in IoT security.